So I'm Nick Jansma. It's probably Jansma, but I grew up in the United States, so I don't speak any Dutch, unfortunately. As Steve said, I work at SOSTA. I work with Philip here. We work on Impulse. And today we're going to talk about forensic tools that we use in performance investigations that we do. Let's see, there we go. That's us. So we have a product called Impulse. Impulse is a real user monitoring tool. So we gather performance data from real-world page loads, and we beacon this data back to our analytics service, so all of our customers get real good performance data. And I'm going to apologize ahead of time. I have a bit of a cough going on right now. So
we've actually been doing back-to-back talks since Monday, and we haven't slept since Sunday morning.
Apologies.
It always goes well at that point.
So yeah, the biggest thing is that we have this JavaScript, Boomerang. It's a library. It's an open source library. We'll go into it a little bit more. A lot of the stuff that we're going to talk about today are because we are a third-party script provider. So our customers include Boomerang on their pages. And Boomerang then gathers these performance metrics and beacons the data back to us. And because of this, we see all sorts of issues. From performance issues, people think that our script's causing problems, and we're trying extremely hard not to cause any issues on any of our customers' sites.
Yeah, it's very important if you're the person who's measuring performance and helping people improve performance, that you not be the cause of the performance problems. So we take that very seriously.
We have to prove it over and over and over again. And some of the tools that we're going to look at today help prove that. They help prove that we're not causing other functional issues and stuff like that. So we actually serve Boomerang from a CDN to our customers. So they include a little snippet on their page. It's a non-blocking JavaScript loader snippet. And yeah, as we said, it's extremely important for us that we don't screw up, because we could screw up our customers' sites because it's JavaScript in their page. So Boomerang was created by this gentleman to my left when he was working at Yahoo. It gathers performance metrics in the wild. It's open source today. SOSTA contributes to it quite a bit. Sorry. Just click away from it. It'll be fine. Yeah, it's not working. Sorry. It's open. Oh, sorry. It's open source. SOSTA contributes to it quite a bit, but we have other people that contribute to it as well. You can use it. It'll gather all this performance data on your sites as well, and you can beacon it back to whatever backend server that you want for analytics. It's available on GitHub there. And as we mentioned, we have Philip actually helped create this non-blocking script loader pattern. A couple years ago, he blogged about it. I think he talked about it at Velocity as well.
Yeah, I've spoken about it at Velocity before. The idea is basically when you load your JavaScript, to take it out of the critical path so that it does not block the host page, even if your JavaScript doesn't actually load. So if there were a problem with our servers were down, or we had like 3-minute latency, you would not notice that on your site. So we can go down, we just won't bring you down with us. And that's very important, that we not be a single point of failure. So we should also mention that while many of the things we figured out are because of our script and because we've been using this, they actually apply to anyone. So just because we found it out with Boomerang doesn't mean you have to be using Boomerang to use these tools. Right? You can be using it, the techniques apply to any other tool that you might use.
We just happen to wade in it day to day, and we have to redo the same investigations over and over again, so we've gotten pretty familiar with a lot of these tools, and we hope that you'll be able to find the same utility out of them as well.
So this is actually the snippet that we use to load the JavaScript. There might be some familiar parts where we actually, if you notice, we create a script node and add it to the DOM. What we also do is we create an iframe and add the script node inside the iframe. And when we create the iframe, we actually assign JavaScript:void 0 as the URL. I think I'm blocking the screen. Can everyone see the screen? So don't worry about the source code. The slides are available online, so you can actually see the source code there. But essentially, we create this URL called JavaScript:void 0. which essentially tells the browser to create an iframe with nothing in it. And when it does that, what happens is it fires the iframe's onload event immediately. And whenever the iframe's onload event fires, the iframe is no longer considered a blocking resource for that page. Then you can go ahead and add more resources to the iframe, and it won't actually block the host page. So that's an awesome way of loading content asynchronously and in a non-blocking manner without affecting the host page. A lot of the other code in there is complexity, just in case the host page changes document or domain. So whenever you're dealing with iframes, you get into cross-domain issues if the two domains don't match. So there's actually about 30% of the code in there is just to make sure document or domain matches across the iframe and the host page. There is a separate 45-minute talk that goes into just that snippet. We won't be going into that today.
Yeah, so the whole point of this talk is we have a lot of customers that come to us with questions or problems or concerns about either what we're doing or what Boomerang's doing or other issues that they're having with their site. And at the end of the day, what do we do? Well, we bust out our favorite perf tools. Here's some of them, some logos. We're going to go through, I think, about 10 or 12 of them through the course of this talk and kind of give you, ideally, you've probably seen some of these tools. You've probably used some of them. Maybe you haven't. Maybe we'll show you some new features that you haven't used before, and hopefully just kind of add more things to your tool belt. OK, so we have 5 scenarios that we're going to go through. This is the first one.
Should I take it?
Yeah,
All right.
Go for it.
So before we get into that, how many people here are JavaScript developers? How many people are ops people consider themselves doing ops as part of their job? All right, so there's actually a good balance, maybe about 50-50. So this might actually speak to both parts of the audience here. So I've just been talking about, right? We say that we've done all of this work to make sure our snippet is non-blocking, yet somebody comes up and they've run these tests and they see something that looks like this, where our script loads, and it takes a long time to load, and then all the other resources show up after that.
This script, c.goimpulse, may be hard to see. We'll highlight it throughout, but this is our third-party script.
Right. So c.goimpulse.net is our third-party domain, and our customers all include a script from that domain. So if you were to show me this kind of waterfall, and if I did not know that it was Boomerang, I would say that this is the script that's causing the problem, right? Would anybody say otherwise? If you saw a waterfall like this, would you say that, no, this is not the problem, something else is the problem? Right? It seems pretty obvious looking at that. And in fact, there wasn't just one waterfall. They sent us several waterfalls. Many of them pointed to exactly the same issue.
And this is a customer, too, that's very performance-focused. He does a lot of his own investigations. And the quote on the last slide was, if this is true, my team will hang me up by my heels, right? So we want to make sure that...
Yeah, we want to make sure he doesn't hang by his heels, because then we lose the contract. Right? So anyway, they sent us many different screenshots, which kind of showed the same issue. And if it were anything else, I would say that's the problem. But because we spent so much time trying to make sure our script was non-blocking, my first thought was, I don't believe this. Something else is happening, and it's lying to us, right? The waterfall is lying to us. So how do we actually go about, first testing whether this is true or not, and proving what happens? So first thing we need to do is actually reproduce the issue. And now, all of this was run by the customer using WebPagetest. Who here has used WebPagetest before? Awesome. Not everybody put their hands up, but most of them did. So WebPagetest is really good for reproducing real-world page load scenarios. You can select different browsers, different kind of connection types, different locations of the world, and run tests against your website using those scenarios. And it's great for testing single points of failure. It's great for giving you waterfalls, breakdown by TCP, looking at different domains that you're connecting to, and tells you a lot about your page from these different scenarios. Right? So WebPagetest is a great tool. We use it a lot. Our customers use it a lot. And if WebPagetest was saying that this is a problem, then there must be something we could do about it. So the cool thing about WebPagetest is every time you run a test, it creates a URL that you can go and visit later or share it with somebody else, and they can see the results of that test. So our customer shared with us all of the test URLs. which meant that we could go in and look at the test in detail and see what was actually causing the problem. So we looked at that. There were 9 runs, and 2 of them pointed to our script being the problem. Right? So exactly like this, there was c.goimpulse.net, which had a long load time, and all the other resources started after that. WebPageTest also shows you other things like CPU utilization and bandwidth utilization below the waterfall, so you can look at that to tell what else is happening on that particular host while this test was running. So this was the first repro. A larger view. Again, it looks pretty clear from here. There's a lot of things happening before, then our script loads, and then a lot of things happen after, and nothing happens in that time when our script is loading. The second case is almost the same. There's a few other scripts that also have scripts or images or something that have a problem, but it seems that our script is causing the blocking for everything else. Right? So this is kind of getting suspicious, and it's at this point that we also started looking at CPU and bandwidth. So if you notice here, CPU is kind of pegged at 100% for quite a while, and bandwidth is at 0 for quite a bit. And if we go back, so go back to the previous one, we kind of see similar situation here, that CPU is also 100%, bandwidth is 0. So something is happening that's sending the box to 100% CPU and bandwidth to 0, and we don't know what that is. It could be our script, right? It could be that our script is not actually blocking, but it's taking a long time to execute, and that's what's making things slow. But we needed to investigate. So the next thing was to dive deeper into it. So like I said, we found CPU being 100%, bandwidth being 0, and this happens for a long period of time, to 1 to 4 seconds in that page load scenario. So there's nothing happening in that time. Nothing else is downloading. The browser is just too busy to do anything. And we wanted to find out what was actually causing this, but also, well, was our script involved? So our primary motivation was our script involved in this? Secondly, if our script is not involved, what is involved in it? So we looked at also the non-repros. Like we said, there were 9 tests. 2 of them pointed to our script. 7 of them did not. In all of those cases, all of those other 7 cases, Boomerang itself loaded pretty quickly. But again, there was this period of high CPU usage and 0 bandwidth usage. So other scripts were delayed, similar to how Boomerang was delayed. And we needed to find out why. Some more of these screenshots here. So who has gone beyond the waterfalls in WebPageTest? Right, far fewer hands up. So whenever you run a web page test and you get your waterfall, look on the left pane. Right? There's all these different things that you can click on there. So go ahead and click on them.
And it's dependent on if you're using IE or Chrome. Like in this case, Chrome will give you more options. IE may give you different options, just depending on what they export.
So one that I really like is the tcpdump, which gives you a packet capture. So while WebPageTest is running, it also runs a packet capture using tcpdump to see what's actually happening on the network. And it pulls all those packets and saves them as a pcap file. Now there's 2 ways to view that. You can either download the pcap file and view it using tcpdump or using Wireshark, or you can view it online. There's a tool called Cloudshark, right? Cloudshark has recently changed their license, so the packet capture files that are created by WebPageTest are now too big for the free version. So I would recommend just installing Wireshark and testing it locally. And I'm actually going to show you how to do that in a bit. There's also a few others. There's a timeline view that is based on the browser. So like Chrome shows you a timeline of what's happening when for the page load. There's traces and network logs. So let me jump straight into Wireshark right now. Right. So what I have here is Wireshark. I've opened up the packet capture file. It's pretty easy to open. You do file open and select the packet capture file. If it's installed correctly, you might even be able to just double click on the pcap file and it'll open it up in Wireshark. And what it does, it shows you all the packets here. So right now what we're looking at is, well, we're looking at every single packet that was captured by that WebPagetest box. Something interesting we noticed there was that Pat Meenan's TiVo running in his master bedroom was also scanning the network. And we picked up those packets as well. So maybe it was his TiVo that was causing the test to be bad, but we could not prove that. Anyway, so how do we actually use Wireshark, right? It's great to be able to see all these packets, but there are literally hundreds of thousands of packets, and I cannot go through them manually one by one. So now fingers crossed, because this thing crashed 3 times before we started the presentation, so let's hope it doesn't crash now. So the first thing I want to do is isolate just the requests that I think are causing the problem. Now, I know that the host name was c.goimpulse.net. So what I'm going to do is try and filter on HTTP host c.goimpulse.net and hope it doesn't crash. All right, it did not crash. So I've basically got 2 packets where there was a request made to c.goimpulse.net. They were both HTTP requests because my filter is http.host. So it's implicitly filtering to only HTTP requests and ones which have a host header in them set to this particular value. So now this itself is not very useful, but what it does is it tells me what IP address that host was mapped to. Now c.goimpulse.net points to many IP addresses. So I need to know which IP address was being served by this particular, was serving this particular request. So in this case, I have 190.93.244.15. So what I'm going to do is change my filter to ip.address is equal to this. And this will now show me all traffic between that particular server and this client, right? Whether it was TCP or HTTP or any other protocol. In our case, it will only be TCP or HTTP. And it'll show me all the packets that went to and fro. So now I can start looking at these one by one. And so who here knows how TCP works? OK, so I'll just explain very briefly for those that don't. Whenever you set up a TCP connection, what happens is the side initiating the connection. So important to know that in the case of TCP, there's no client and server. They're all peers. So one end initiates the connection, and the other end agrees to connect to it. So what happens is one end sends, and in our case, it's typically the side that wants to request the web page that initiates the connection. So that will send what's called a SYN packet, saying, I want to synchronize with you. So that's what you see here, a SYN packet. And then the other side responds with a SYN of its own and an ACK. An ACK saying, I acknowledge your SYN, and it sends a SYN of its own. And then the first side sends an ACK back saying, I acknowledge your SYN. And at this point, it's called a 3-way handshake. A connection is established. Once that connection is established, the side that initiated, that wanted the page, can actually go and start its HTTP request. So it's now made a TCP connection, and it sends an HTTP request over that TCP connection. And that's what we're seeing in here, is we're seeing a get, boomerang, and the file name there. We can go ahead and explore that in Wireshark. If I expand that hypertext transfer protocol section, it shows me the entire request here with all the HTTP headers. And so an HTTP request just contains the headers and a new line character to show that it's ended. And then what happens is the server starts sending its response back. So the first thing it'll do is acknowledge receipt of this particular request, and then go ahead and start sending data back. So we can see the first segment of data here. Where is that? So I'm not sure if you can see it. I'm going to highlight it here. So this is embedded inside a TCP packet. There's HTTP/1.1, 200 OK, date, and all that stuff. So there's actually HTTP headers embedded inside that TCP packet, right? It's not a complete HTTP response. It's part of a response embedded in a single packet, typically about 1460 bytes long. So the entire response might be much larger, might be, let's say, 100 kilobytes, but it's going to be broken into these 1460 byte packets, because that's how much is going to fit in a TCP packet. And you're going to send multiple packets. So we're going to get multiple of these. And I'm not going to go into each of them because the content is gzipped, and I'm not very good at unzipping using just my eyes. So what we're going to do is skip right ahead to where Wireshark reconstitutes the response. So Wireshark has this cool thing. It'll insert these dummy packets into its view. So once it's got all the TCP packets that were real packets that came through on the network, it'll recombine them into a single HTTP response because it knows that these packets are part of an HTTP response. And it'll show me what that HTTP response looks like. So in this case, it's showing me the entire HTTP response here. And I can look at that. So I see it's split out all the headers in there. And it's also going to show me the content, but because it's gzipped, I can't actually decode that. So I won't worry about that. I know that something has happened. So the important thing that I want to know is, remember when we saw that waterfall? It showed that it was waiting for something, what was it, 1.5 seconds or something? A fairly long amount of time. So let's look at the time difference between the request and the response, right? So I have the request here that's at 30.93 seconds. So 30.93 seconds from the time the packet capture started. And I have the response, which was completed at 31.01 seconds. So how many milliseconds was that? 31.01 minus 30.93 is about 80 milliseconds. There's a big difference between, is that right, 80 milliseconds?
Yep.
There's a big difference between 80 milliseconds and 1.4 seconds, right? So why is it that it took 80 milliseconds for the response to get from my server to the client, sit in the network interface? So it's reached the network interface, it's reached the operating system, it's already there in memory, but it's taking 1.4 seconds from that point to get to the browser. What's happening within the box, right? Something has gone wrong, and it's definitely not my script, because my script is loaded. It's not my script that's blocking that. So what actually is the problem? One of the other examples we looked at pointed to DNS being a potential problem. So maybe it took a long time to do a DNS lookup. So the cool thing is we can use Wireshark to also figure out how much time was spent in DNS. So to do that, what I'm going to do is go back to the first packet. That's when my TCP connection was initiated. What happens immediately before the TCP is the DNS lookup. So I'm going to clear the filter now. And there are various ways of doing this. I could use a filter on DNS itself. But I find the simplest way is to just get rid of that filter and see which packets are just before that. That's a DNS packet, that's a DNS packet, that's a DNS packet. I think this one is, yep. So this is the one I care about. It's the response to the DNS request. And notice this cool thing Wireshark has done is it's put this little dotted line saying where did the request start. So the DNS protocol is UDP based. There's no actual request and response. There's a request packet sent, and at some point later a response will come, and it's up to the application to figure out which request matched which response, and it does that using its own internal mechanism. So it's not like TCP where there's a session set up and stuff. So in this case, Wireshark, it also does that kind of deconstruction and reconstruction of the packets to tell you which packets are associated with each other. So I can see here my request went out saying, tell me who has c.goimpulse.net, and the response comes back saying c.goimpulse.net belongs to this, is a CNAME for this particular host name, and so on. But what we care about is the timing, 30.87 here, 30.89 here, 20 milliseconds between the two. So clearly DNS was not a problem here. So 20 milliseconds for DNS, 80 milliseconds for the HTTP request, including the TCP handshake. Actually, did I include a TCP handshake? I don't think I did. I did. So all of that does not amount to 1.4 seconds. Something else happened, and that's when we start looking back at the CPU spike that we saw. So the CPU spikes that we're seeing here, all over the place. And when we started looking at this in more detail, we found that the spike started much earlier.
It's kind of hard to tell, but this is actually like 100% CPU right here. The orange line is at the top of this.
So let's actually go back to some of the, yeah. So this one might be a little easier to see. Do you want to give me the pointer?
Yeah.
So the boomerang request starts around here, which is just before the 2-second mark, but the CPU spike happens right here around the 1.2-second mark. So it's happening way before boomerang loads, and we try to correlate what actually was loading at that point of time. And we have theories. We cannot point our fingers directly at one thing. So some possibilities are the particular VM that was running this web page test must have been busy. Maybe it didn't have enough. Maybe there were a lot of other VMs running at the same time. Another thing we noticed was a lot of tag managers. So in this particular case, this site used more than one tag manager. They used like Google Tag Manager plus BrightTag plus TagMan. So each tag manager is probably built well to know how to manage resources to download only a certain amount of things in parallel. But when you put 3 of them together, they don't talk to each other. So now each of them is fighting against the other to download things in parallel. And that itself, sort of adding all of those nodes together, could shoot up bandwidth usage and could also shoot up, bring down bandwidth usage and shoot up CPU usage. So those are our theories that it's possibly one of these things, and a good way to prove that is to make one of them a SPOF. Right? So I think we talk about SPOFs later, right?
Yeah.
So let's first talk about the processing breakdown, because this kind of leads into what actually the CPU being spent on. Do you want to take this over?
Yeah, sure. So from WebPagetest as well, you can get this processing breakdown. So this is for the browser, where it was spending its time, both CPU-wise and elapsed time-wise. Sorry, it's hard to see, but 2 of the key takeaways. So the yellow block right here, this is scripting. So somewhere like 58% of the time is spent in JavaScript on the page. You get a breakdown of all the other components. So there's layout and rendering and parsing and stuff over here, and then specifics of the processing over here as well. Now, from a elapsed time point of view, you get a very similar breakdown as well. The gray part over here is idle time, and the yellow part over here is scripting. So overall, the page was idle a lot, not doing much, even though we clearly saw the CPU was pegged for a long time, so we don't really know what's going on there, but we can dive into that in a bit.
It was very busy doing nothing.
Yeah, but still, a lot of the page is just scripting or doing nothing, right? We already talked about TCPdump. Have you guys ever actually tried to capture a TCPdump PCAP before? Yeah? It's really hard. I don't know.
Let's actually try that. So with Wireshark, I'm not going to go into tcpdump right now because I don't want to remember all of the command line parameters. But with Wireshark, it's kind of easy. We can actually just start from here, I think. No, interface selected. Do I need to clear this up? You know what? Yeah, capture. Start. I got it. Oh, yeah. So the way I do it is just start Wireshark from scratch. All right, and when I do this, I can select an interface. So let's say my Wi-Fi interface, and then I start capturing. So just double click on that or something, and it starts capturing packets. So right now, what it's there are several ways to run this, and right now it's just capturing all packets that are coming into my system via the Wi-Fi interface, the EN0 interface. You can select which interface you want. You could also tell it to go into promiscuous mode. The promiscuous mode basically says don't listen to only packets addressed to you. Listen to any packets that you can see around you. So if you're on a wired connection, typically connected to a router, you can only see packets coming to you. But if you're on a Wi-Fi connection, you can see all the packets that are in this room, right? All the packets going between the local access point and any machine in the room. So you can actually capture that and sort of analyze somebody else's packets as well. And once you've done this, let's stop it now. It's already picked up 6,600 packets in the time I've been speaking. And then we can go ahead and apply all those filters that we were talking about. So in this case, we can see if there's any HTTP hosts that have been looked up, or There's a lot of DNS lookups and stuff that's been happening. A lot of IPv6 connections, which is interesting. So do you know if the access points here support IPv6? Does anyone know? I don't know. So, all right. So, well, that's the easiest way to start a packet capture. And there are obviously many capture filters. So if I go into capture filters, I can select what kind of things I want to actually filter on. So these are examples. Filter only on this Ethernet host. If I take out that, it'll basically turn into promiscuous mode. Which protocols? So in this case, we say don't collect broadcast and multicast packets, but I might want to do that if I'm actually studying broadcast. Look at TCP or UDP only, etc. Right. So back to the slides.
So tcpdump is like the base for what generates a lot of these capture files. So Wireshark has its own, probably calls into libpcap, which helps generate these captures. I'm sure WebPagetest uses something similar as well. Okay, so we looked at Wireshark already. This is an example from the repro, the bad page load from us. In this case, I forget what we're seeing here, but
so we see the actual request there.
Oh, this actually isn't the repro. This is just something else. This is just a screen capture. Sure. Cloudshark we talked about. Right. It's a way of viewing PCAP files in the cloud.
Cloudshark looks very similar to Wireshark, except it's all built in HTML and JavaScript and CSS. And like we said, it no longer supports the size of PCAP files that WebPagetest generates.
I think it limits at 2 megabytes.
2 megabytes. And WebPagetest goes a little over that. So we used a 1.9 megabyte packet capture file to get the screenshot.
You can actually trim it from the command line, too, just to put it into Cloudshark if you want. But yeah, so at this point, we want to figure out what else was going on. Here's, if you go down one, here's another example where we actually didn't see any packets on the WebPagetest machine at all for nearly 1 second. And that's just kind of weird, right? There should be a lot of activity going on. Right. There's a ton of different connections open to all these different hosts, and there was no activity for an entire second.
So you saw when I ran the packet capture right now live, within I guess about a minute, it had already captured 6,000 packets. Whereas in this case, to go an entire second with no packets anywhere, that's very suspicious. Something has gone wrong somewhere.
Either something with the network or the machine itself.
Sorry.
So yeah, at this point, we kind of wanted to hop out of the networking side of things and jump into dev tools, right? So obviously, browser developer tools are awesome. All the major browsers have them: Chrome, IE, Firefox, Safari, even. And we could spend an entire talk just talking about dev tools and what you can do in the dev tools, but we're just going to do a couple highlights, especially related to what you can get from WebPagetest, the data that you can pull out of WebPagetest and see in your dev tools. So Chrome has this thing called Chrome tracing. It gives you like really low-level insights into what the browser's actually doing.
It may not be clear in the screenshot, but it's written up there. If you open Chrome right now and type that in,
and it'll give you like a timeline of everything that's going on, from layout to rendering, the stacks for everything that it's doing. So it's a really, really invasive look and see what Chrome is actually doing, and you can use it to understand what's going on with your website. So this was actually from WebPagetest. The trace link is Chrome tracing. So this is a view of one of the repros. This is the timeline from 0 to the end of the test. The stacks are what's going on during the test. So it's really hard to read, but I'll just say there's a lot of like rendering and painting and stuff going on here. But you can see that most of these, the width of these stacks is pretty small. It's in the order of like 10 milliseconds max, something like that. The highlighted region right here, the red region, this is when we saw Boomerang causing an issue. This is when nothing was happening on the machine. We actually see that Chrome was actually doing nothing. The way that we see that is a single width, a single action was happening in Chrome. It was taking over a second to do it. I think this is layout and rendering right here. It should not take that long at all. I mean, layout and rendering should happen like that. So in this case, we actually think there was some sort of contention with the VM that WebPagetest was running on. There was some other activity stopping the actual virtual machine from doing anything. And you can get that just by looking at the Chrome tracing. Here's another view of it as well. Can't even read what it was doing right there, but very similar thing where the width of an action that Chrome was taking over a second, and it's just.
So this was the second repro. The first one was the case where we found Boomerang taking a long time. This is where we found Boomerang and a few other things taking a long time.
And just compare it to the width of all these other operations going on. I mean, these are like really, really, really fast based on the width, and then there's like this one block of nothing happening at all. Also available from WebPagetest is netlog. So netlog is Chrome's network logging tool. It's kind of similar to PCAP, to Wireshark type stuff. I think it's a more summarized version of it. You get everything from like timestamps to what's going on there.
And so it's kind of interesting to compare this with what PCAP tells you, because PCAP is more at a network interface level, versus this is at what Chrome has already got at the browser level. So it kind of gives you that difference between what's already reached the OS versus what's reached the browser and not yet made it to screen.
So we've looked at a lot of different things. And I'll say, like, we did this investigation over probably a period of a week or two. There was 2 or 3 of us working on it nearly full time to try to figure out what's going on. And at this point, we're like, well, we don't really. The
only thing we knew is it was not Boomerang. We did not know anything else about the problem. So
we wanted to prove that. We wanted to prove that if, for example, Boomerang was slowed down artificially, if it it took 30 seconds to download, would it affect our customers' sites? We do not want that to be the case. The loading non-blocking script loader pattern that Philip helped create is designed to not block anything else. So we wanted to do single point of failure testing.
So who's used WebPagetest to do a SPOF test? Cool. So we're going to show the rest of you how to do that.
So WebPagetest has 2 ways of setting a single point of failure for a domain. In this case, our go.impulse.net, our CDN, you can either do it with scripting, which is the very top one, and you can set it to blackhole.webpagetest.org, and that's a server that will capture packets but never send them back at all, so it just seems like it's not responding. Or you can actually do it in the UI as well, which is an easier way of doing it. There's a SPOF tab, and you can just put your host names in here. And then WebPagetest will run your site with that domain not responding at all. So this is the results of us running with our domain, go.impulse.net, being single point of failure, which means it did not respond. At the very top is the, so these are film strip views of the page load process. The top one is normal, so not blocking anything. And the bottom one is single point of failuring things. The timeline's the same. The difference here is extremely minimal. And it's just kind of random variation that our single point of failure test actually was slightly faster than our non-single point of failure test. But we ran this a couple times, and if we were a single point of failure, this would be completely different. The load of the original one would be over here, and we'd be way out here at 30 seconds.
So it's important to note what black hole does is it doesn't just reject the connection. So normally if you did not have a server, it would reject the connection, and that would fail immediately. Black hole just doesn't fail. It just waits until the TCP connection times out, which by default would happen at 60 seconds. So what you would expect is to see nothing happening for 60 seconds and then something showing up if, in fact, we were a single point of failure.
So that's one way of doing single point of failure testing. You can have a service like WebPagetest do it for you. But it's also good to prove it on your local machine. On your developer machine. And there's a couple ways of doing this. One thing that we're going to touch on again, obviously, I think most of you guys have seen a waterfall in the browser developer tools. Yeah, know what waterfalls look like. So all of the resources in a list. This is actually not a very good waterfall because it's so scrunched up, but the timings of it, we talked about them earlier, obviously.
Yeah. So the reason for this is with WebPagetest, you get the waterfalls built into WebPagetest. When you're testing on your local machine, you need to have those waterfalls in your browser, and then you use that to compare the before and after.
And all the all the developer tools have their own versions of Waterfall. That was Chrome's. One way of doing single point of failure testing is just modifying your etc hosts. So this is on Mac or Linux.
Who's familiar with the etc hosts? Good.
Did you know there's one on Windows too? Yes. Okay, that's where it is. C Windows System 32 drivers etc hosts.
So Nick uses Windows, by the way.
I'm the one Windows guy here, probably. So yeah, but you can use it for basically doing single point of failure testing as well. Look up blackhole.webpagetest.org. This is the IP address. I don't think it's going to change, but just look it up if you want to do this. And then you just set all of your domains that you want a single point of failure in etc hosts to that IP address. So then anytime you're actually trying to load your domain or Google Analytics or whatever, that request will be blocked. That's a pretty easy way of doing it.
So I actually permanently do this for some domains that I don't want to ever return content.
Some ad blockers do that, basically. Another way of doing it is a tool called Fiddler. How many of you have used Fiddler? Oh, good. All right, cool. So Fiddler's great, and we're going to go over a bunch of different ways to use Fiddler today. One of the ways is single point of failure monitoring. So Fiddler is a proxy. It's an application that you can run on Windows or Linux or Mac. The Mac version isn't as good, and we're hoping that they're going to actually develop an actual Mac version soon. But it's a proxy where you can see all the traffic going through to your site. You can modify it in real time. You can block things. You can delay things. It's a very powerful tool for investigating what's going on your system, and not only from your browser's point of view, but any other hosts on your network can go through Fiddler. So, for example, you can use your tablet or your iPhone to go through Fiddler, and you can actually inspect your mobile traffic, which is wonderful, including HTTPS traffic if you import the root certificate that it exports. Screenshot of Fiddler. Can't really tell what's going on there.
There's a question back there.
Yeah. So the question is, have we played with the Fiddler core library? So Fiddler, the author of Fiddler, it's currently owned by Telerik. Eric Lawrence was the original author of it. He also has a library called Fiddler Core, and for Windows, you can actually include Fiddler in your application if you want. You can tell it to do things. So I've actually wrote a plugin for a Selenium test that also captured Fiddler traces as well automatically. So anytime any failures happened in our unit testing, we also got a waterfall of what was going on at the same time. But it's basically all the non-UI stuff of Fiddler in a library that you can import and use. So it's really powerful. This is the UI. Basically, this is a list of all the resources or all the requests, HTTP requests that are happening on the machine in real time. And the other panes can let you inspect the data, modify the data, etc. For single point of failure testing, it's really easy. So there's this auto responder tab. And you can basically apply a regular expression to the URL that you're interested in. And then there's this special syntax, *delay:*, and then how long you want to delay it. So in this case, we're saying delay all responses for our script by 30 seconds. And this is what it looks like in a browser waterfall afterwards. So the highlighted resource right here is us, our script. These are all the other resources, and we see that we are not blocking anything below it. We are using the asynchronous script pattern to not block other things. So this, you see the same thing with the etc host changes. We've proven on our local machine and via WebPagetest that even if our script is blocked or delayed, we're not going to cause other issues. So at the end of the day, what does this all mean? Well, we've shown that there were some funky things going on with WebPagetest that day. It could be related either to contention on the virtual machines that WebPagetest is running, maybe exacerbated by the fact that there's all these tag managers kind of loading at the same time, causing high CPU and low bandwidth. We've proven that even if you're to take our script out of it and single point of failure it, that we're not causing the issue. And basically, we were able to give all this data back to the original customer and prove that we weren't causing problems.
So I think for us, actually, the biggest takeaway was that we probably spent 7 man days on this or more, which is quite a lot of time just to be solving this one problem. But at the end of that, we figured out how to use all of these tools. So when a problem like this comes up again, it's pretty much a 10-minute job to figure out what the problem is, or at least disprove some scenarios and prove other scenarios. So we know we can start off with Wireshark. We can go into the Chrome tracing library. We can use Fiddler. We already know where to put the breakpoints, where to put delays, and actually figure out where the cause of the problem is. So I think for us, using all of these tools really helped a lot. We're going to go into a few more tools now.
And Steve?
Yeah. So this is not the end of the talk, right? Just the end of scenario 1.
We have 5.
Was your customer satisfied with your explanation?
Yes.
Yes.
We put a lot of energy into convincing them with all these charts and graphs.
So
at the end of
it's
the
also
day,
important to note that they were unable to reproduce it ever again.
yeah.
So
We could reproduce it that day. We ran an independent WebPagetest that day, and we saw it as well. But we tried again next week and later.
And
didn't see it
we also
again.
collect waterfalls from RAM data, and we could not see any of these blocking issues with the RAM waterfalls. Did you have a question? That was the question? All right. I knew that was the question. Barry.
Assume you're using public web page test for this scenario,
Yeah.
Try on the same day using a private instance to see whether you could kind of pin it down to
So,
actual host of web page test.
so the question was, we've been using the public web page test instance, and did we try using a private instance to pinpoint whether it was in fact a web page test problem or a host problem, sort of run some other traces? The answer is no, we did not do that. We don't have our own instance, right?
We don't, but that's a good idea, and we will
Yeah.
put that in our back pocket for next time this happens.
So that's going to be the next slide. The next time we do this talk, there's going to be one more slide.
And another important thing to just for this scenario too, like we went down a lot of paths that didn't bear fruit at all. Like we showed you like our highlights of all this, but when you're investigating things, you're often going to hit dead ends. And using these tools, you can hopefully find that dead end quicker the more you know. Steve, one more
If
question?
you didn't have your own private instance of WebPageTest, can you think of any services that you've used?
Yeah. So the question is, if we or whoever's doing this did not have their own private web page test, are there other services that do that? And yes, there are a few companies that do that commercially. So do you happen to know one of them? Talk to Steve. He has business cards. All right, scenario 2.
You want to take it?
All right, I'll take it. Since Nick did this last time, so I'll do it this time. Pre-render. Who's familiar with pre-render? Awesome. So maybe I should explain what pre-render is first. So particularly Chrome. Chrome is the first browser to implement pre-render, and what it does is it can download a page, execute the JavaScript, render it, lay it out, and keep it available for the user when the user requests it, and by knowing in advance that the user wanted that particular page. Right. Other browsers also do something similar. For example, in Safari, to display the recently viewed web pages, to display a preview of that page, it might pre-render a page to actually display it there. And I think Internet Explorer had plans to implement pre-render the same way that Chrome does, but they haven't implemented it completely. So if you sort of search for a page on Google, typically, I don't know if it happens in all cases, but the first result might be pre-rendered. So if you click on that, it might sort of display immediately rather than going through the whole download process. So the case we saw here was the customer was saying that they saw pages that should have matched a particular pattern by our analytics tool, but did not actually match it. And they were breaking their heads on this, and why was the particular regular expression for that URL not working? And they told us about the problem, and we tried to figure it out as well. So this is a screenshot from the Impulse tool for defining regular expressions to map a URL to a friendly name. So for example, you can define a product page or a category page or something like that using a regular expression. And typically, if a user visits a particular URL that matches that expression, it'll map it onto that friendly name. And the case here was that there were certain URLs that should have matched. That whenever we tried it manually, it did in fact match. But when we looked at the analytics tool, it wasn't matching. So something was going wrong, something in Boomerang or something in our analytics tool that was causing this match not to happen. And we wanted to figure out what. And we'll fix it. So we had to get into RUM tools. And it just so happens that we write our own RUM tools, so it was fairly easy for us to change the code that was going in there and to sort of test things out. So how do we do that? So RUM lets you view all your real-world data, right, and aggregate it across multiple users. So we found that in most cases this particular mapping was working, but in some cases it wasn't, and a very small minority of them. And really, when you start looking at data and you find like 3-4 outliers, you really can't rest until you figure out why those are outliers. Even though you've got 1 million data points that work perfectly well, you have to solve the problem for those 3 that don't. So this was the particular path we went down to figure that out. So what we started doing was, since we have this RUM tool, we have a lot of dimensions coming in on the data, which include things like which browser was it coming in from, what type of HTTP request was it, what time of day, which country, which operating system, all of that we knew. So we tried looking at that data in more detail only for these outliers compared to everything else. And some things kind of stood out a lot. Like iOS mobile Safari sticks out a lot, and iOS sticks out a lot. So the blue here is mobile Safari, the blue here is iOS, and what was that? Chrome Mobile is the second one? Yes, Chrome Mobile and Android. So they're mainly mobile browsers, but iOS Safari seems to stick out more than the others. And also by looking at RUM waterfall. So using the resource timing API. Is everyone familiar with the resource timing API? Right, I see people nodding. So the resource timing API allows you to collect waterfall data from pages as users are browsing them. So we collect all of this data and we generate our own waterfalls. So from that we also saw matches where there were very few cases where this URL should have matched but was not matching. And we tried to find out, well, was something happening, right? At what point of time was it rendering? When did onload happen versus different other custom timers? So we tried and figure out what was common between them. And it was really hard. Because there were so few data points, it was really hard to do it. So we had to come back and try and reproduce it ourselves. So how do you reproduce visiting a URL and seeing what's happening? Right. Well, you keep typing in the URL, hitting enter, and seeing what happens on the network. And you keep watching the network tab and trying it over and over again and getting really frustrated. So luckily, I had Nick to do this for me. I didn't have to do it. So I did not get frustrated. So Nick kept doing this, and testing these things out on an iOS device is not easy. Have you tried typing a URL in an iOS device? Right. So it was not a fun experience, and we needed something better to do this. So time to reproduce it on an iPad. Now you can do a bunch of things, right? You can plug your iPad into your laptop and sort of type in the URL using the Safari's web developer tools and stuff. Or you can use JavaScript to drive the URLs. But none of these actually caused reproductions. So this is a great use of Fiddler. So you put Fiddler as a man in the middle. Let Fiddler sit between your iOS device and the server. And then you don't have to worry about browser dev tools. Have you tried using iOS browser dev tools? They don't actually exist on iOS itself, right? They exist on Safari, and it's very hard to actually debug something easily this way.
And they seem to crash a lot too.
Yeah. So using Fiddler as this man in the middle gives you a great way of looking at the waterfall and even changing what content is being served or changing how fast it's being served. So we started looking at that and looking at the actual page groups that were sent across. So in this particular parameter, Fiddler has this option of splitting out the URL. So you can specify which query string parameters of a URL you want to see, and it'll show you those as a separate column instead of just showing you the whole URL as an opaque string. So in this case, we could do that and keep testing and just looking at that one field to see, well, when does it show up as no page group versus showing up as the intended value. And
the other big thing here is we actually put a filter in Fiddler to only look at the specific traffic that we want to look at, so just our beacons that's sending the data back to our analytics server. So you don't see this huge list. I mean, it's just like a filter in the Chrome DevTools, right? But we added the domain filters, added this column, and then basically we just had to watch this column to see when we had the repro that we wanted.
so at this point, we, meaning Nick, sat with an iPad and kept reloading the home page over and over again, trying to reproduce this.
I literally sat there probably for about an hour typing in, www.customer.com, go, nope, www. It took a long time. And then,
Why not paste
good point,
it?
I'll do that next time. And then I got a phone call.
So
right
the
in
problem
middle.
was pasting it may not have reproduced it.
Yeah, that's true, actually. I got a phone call right in the middle of when I was typing it. So I answered the phone, hadn't hit enter yet, and I saw a beacon come through. So we hadn't gone to the customer site yet, but our script was running, and our script was sending something back to us.
And here's the interesting thing, because our script is actually recognizes pre-renders happening when Chrome does it. And it says, I know this is a pre-render, so I'm not going to fire a beacon because the user hasn't seen this page yet. But this was something different. It was happening on iOS, which we know does not support pre-render, or at least we thought did not support pre-render. Yet a beacon was being fired before the user hit enter, which pointed to pre-render. And Nick basically asked me at that point, hey, does iOS support pre-render? And I said, not that I know of. And he says, well, maybe you don't know enough. And so he started looking at it in more detail. And it turns out that mobile Safari was, in fact, pre-rendering the page. So normally when you type in a URL, you notice that the browser starts to autocomplete the URL because it kind of knows what you're going to type based on your history or based on the most common, at least Chrome knows from search history what are the most common URLs starting with a particular string. So it'll try and autocomplete. Safari was going one step further and not just auto-completing the URL, but also if it was already in your history, it was going to go and pull it out of page cache and render it and fire the onload event, which in turn would fire the beacon. And this was not expected, right? So we had the render, the reproduction. We needed to investigate a little further. So it could have been a bug in Boomerang. Or it could be that, well, Boomerang was not, didn't know enough about this browser to deal with its state transitions. So the fix was straightforward. We found that there was the onload versus the page show event.
Yeah, we had a bug in our script.
Yeah. So we managed to fix it. The problem is, how do you test this out? Because it's happening on a customer site. The customer has control over the HTML. We don't have control over the HTML. We can change the JavaScript that we serve, but if we change that, it's going to go out to all of the customer's users, and we can't do that in production without testing. So how do we test in production without affecting all the customer's users and without changing the customer's HTML? Right. So another great use of Fiddler, and this is one of the tools. There are other ways you can do that. Is you could remap DNS. So one of the things I do often is I'll change c.goimpulse.net to point to 127.0.0.1, and I'll have my own web server running on my box. So anytime I visit a customer's site, it'll actually go to my server instead of going to or rather come to my box instead of going to our CDN. So I can serve my own JavaScript file to me and not to anyone else. So it's a great way for me to test new code without pushing it out to anyone else. Why are you laughing?
They're going to poison your clients if you got mistaken. Poison their data.
Poison my clients? My clients
So
will just go to their own 127.0.0.1.
So Andy pointed out that we could actually be poisoning our client's data because we're actually generating data and then still sending the data back to our servers at the end of the day. That's another reason why we use Fiddler. Actually, we black hole our own beacon data when we're doing this. So any data that we send out, we actually don't. It doesn't go out to our live infrastructure.
Yeah, right. So if I change c.goimpulse.net to 127.0.0.1, I also change the beacon server to 127.0.0.1. So everything comes to me. So in this case, Fiddler was the easier to use tool. We didn't have to mess around with DNS and wait for that. You always forget that you've changed EDC hosts and get unexpected results. So having this open in front of you, you set an exact match on the particular host name, so only match for this particular host, and then remap this particular regular expression to something else.
And there's a lot of other proxies that you can do this with too. There's Charles, there's Squid, and stuff like that. So I mean, insert your tool here, but most of them should be able to do this kind of stuff.
So the tools we used to fix this or to figure this out was first we had to use a RUM tool to reproduce, to find out to narrow down the cases that we needed to reproduce. So in this case, using RUM, we figured out that it was very specifically iOS mobile Safari. And so we could use mobile Safari to test out. We actually got the version number as well. So we could narrow it down to that particular version of mobile Safari. We used waterfalls to validate that this problem was happening. And then later on, once we fixed it, to validate that it was no longer a problem, looking at a longer scale of data for real users. And then we used tools like Fiddler to help reproduce and validate the fix. I think one interesting side case that happened very similar to this is, again, we had to test out iOS Safari with a new version of the site. Except at this point, we were all at a conference. We didn't have all of our tools available. And we were sitting in a hotel room. We were not on. So hotel Wi-Fi typically has wireless isolation turned on, which means you cannot connect one device to another device on the same network. So what we ended up doing was having one box plugged in to the wired network and set itself up as a wireless access point, just sharing its network connection. And it pushed out the other box's IP address as the DNS server, as the gateway. And this box would then be running DNS Masquerade and Squid. So when the iOS, the iPhone connected to the first box as its proxy, as its gateway, it got redirected to the other box to serve content. And that's the way we had to fix it. So pretty convoluted setup just to get around the fact that hotel Wi-Fi had wireless isolation turned on. Since that day, I always carry a wireless router with me whenever I travel, so that I don't need to do that. I can plug the router in and do these testing. So that's another tool. Always carry a router with you.
Okay, so another customer issue that we found as well. So we actually went to a customer's site. They had noticed that we were not always sending a beacon, and every page load we should be sending a beacon. We should be sending this performance data back to our infrastructure. And we noticed that when we loaded the customer site as well, it wasn't 100% reliable that we were actually sending a beacon back to ourselves. So what we did is we used Fiddler. We injected a debug version of Boomerang, so an unminified version that has a lot of logging in it as well. So that way we can debug this customer site live with our own stuff. And we noticed some interesting things. So there's this document.ready state, which tells you what state the document's in. Before the onload event, it's loading, and then after it's loaded. And we noticed what was really weird and which should never happen by chance was that document.ready state was loading after the onload event fired. And just that shouldn't be the case at all. And we also noticed some other events were kind of firing out of order. Page show was firing before onload, and it should always fire afterward. So we figured there was something funky kind of going on. Our guess was that some script, a bug somewhere was messing with these document states somehow. Something was getting overwritten. But we had to prove it. We had to figure out what it was, and we had to prove what it was doing was wrong, or screwing with us at least. One way that you can do this, we could have unminified all of the JavaScript for the customer site, but it's megabytes big of JavaScript, and then you got to go and look at all the minified
have you ever
variables.
Tried debugging somebody else's JavaScript?
Not a fun thing at all. We actually used TamperMonkey. TamperMonkey and GreaseMonkey, they're user script managers for your browser dev tools or just your browser. And it basically allows you to inject your own code, kind of like Fiddler does, but more at the browser level, and run code and set breakpoints on that code. And so you can actually put your code into other sites without using a proxy. So we started out with the guess that somebody was messing with the document.ready state or the onload event. And we actually, there's a very, very simple snippet that we use. In order to change the built-in DOM properties like ready state or onload, you can do object.define property. And so we actually overwrote object.define property and just put a debugger statement there. So this is a very easy way for us to see if anybody's screwing with anything kind of like built in the page. This is what it looks like in TamperMonkey. Basically, you tell it when to run, you just put your code here, and you can actually set breakpoints on stuff. Well, in this case, debugger will actually break into a breakpoint if you have the dev tools open. But you will see this injected in the site as well, so you could set a breakpoint. And lo and behold, we loaded the page, and immediately we had a hit. This is actually, we stepped up in the stack in the debugger, and this is the function that was doing it. So in this case, window.onload was being overwritten. And it was, the names have been changed to protect the guilty, but another analytics type, not an analytics tool, a front-end optimization tool was overwriting the onload event with their own event and thus delaying it. Oh, and yeah, by the way, if you ever use the unminify tool in DevTools, it's magic for stuff like this. There's that little
So it always looks like
icon.
this in all browsers. It's always the two curly braces, and you click on that, and magic happens.
And then the magic happens, and you can debug it a little bit better, right?
It means you're not scrolling through a line of 1,500 characters. It's more like a line of 30 characters.
In the same tool, it was actually overwriting ready state. So they overwrote it, and they were saying basically anytime anybody looks at ready state, we're going to return our own property. So they're just like redefining the world of what events happen.
The only thing worse than somebody redefining the world is somebody redefining it backwards. So they're not just changing onload and ready state, they're changing it in the wrong order.
So at the end of the day, we figured out what the problem was. We figured out who it was. We contacted them. All of us scripts on pages have to work together. And we worked out a solution that doesn't cause us to break. So using just simple browser dev tools, we were able to dive into this pretty easily.
And TamperMonkey.
And TamperMonkey.
So a hypothetical scenario, right? What if somebody else was overriding object.define property to prevent this kind of overriding? How would you detect that they were overriding object.define property?
If you figured that out, let us know, because we were worried about that.
We kind of had to figure it out.
Are they screwing if that's there too?
This actually happened when we were doing our talk the last time.
You want to cover this one?
Yeah. This is the crumb one?
Yeah.
All right. So our impulse snippet, what we do is we periodically pull configuration information from the server to figure out, well, has the customer changed their configuration parameters? One of the things that are included on this configuration object is an anti-CSRF token, just to prevent cross-site request forgeries, man-in-the-middle attacks, all of that stuff. So it has a CSRF token, and it has a timestamp token, timestamp along with that CSRF token. And this new token is generated every time a request happens. There is an expiry date on it, so if the token is too old, the beacon will be rejected. And in the case of long-running apps, so typically single-page apps, they will have to fetch many tokens because the lifetime of the page is more than 5 minutes. So we periodically request that, and every time we request it, it's going to take up more memory. So what we try to do is clear up the old memory before we fetch a new config object. So we were finding that when we started doing this, started clearing out the old object, there suddenly started getting an increase in the number of invalid beacons coming through. All of them were being dropped because this anti-CSRF token was invalid or too old, so one of the two cases. And this is typically not supposed to happen. If everything's working correctly, the new token should come in every 5 minutes, and it should just work. So why was this not happening, and why did it start happening after we made this change? So luckily, we store every beacon, even if it is rejected, we store it along with the reason for it being rejected. And so we were able to go and investigate that. And we found, again, we used our tool to figure out, well, what was common between the ones that were dropped. We also had to write a lot of command line scripts. So Nick preferred to do it in Node. I preferred to write it in Perl, Nick 1. And so we ended up writing it in NodeJS. So you can write throwaway analysis scripts. How many people throw away their throwaway scripts? So that got checked into version control.
It did.
That's how we threw it away. Essentially, there's a lot of NPM modules, and if you're using something like Python or PHP or Perl, they each have their own libraries, library networks that have tools that you can use. So in this case, with Node.js, we were able to do some analysis on those logs. So just do a bunch of statistical analysis. We also built one of our own tools, so FastStats, to do statistical analysis of fast statistical analysis of a lot of data. So because this was a large amount of data, what was it, in several
gigs of data.
Several gigs of data, we wanted to analyze it fast. It was easy to use a lot of these tools to just sort of process things in a stream and generate a report out of that. So what did the report look like? Well, what we did was we tried to break down by browser, by OS, by beacon type, and by URL. What we mean by beacon type is you might have beacons that were generated by a full page load, or you might have beacons that were generated because of a single page application, an XML HTTP request, etc. So using all of these dimensions, we kind of isolated it to IE7, IE9, and Safari 5 were the biggest culprits. And IE7 was the biggest of all of those.
The interesting thing here, I mean, this is actual console output, so this is like Node.js on the command line. We used the statistical package, a line-by-line reader that efficiently streams large data into memory. We use this table generator, all to just basically build a mini RUM tool in the command line that we can iterate on really quickly if we need to look at a large set of data.
Right. So the idea was that we could very quickly build a tool to analyze data that we did not have a tool to analyze before. And again, we found this pattern. Who's tried debugging on IE7?
Trick question, you can't.
IE7 has no debugging tools available except for alert.
There's some like third-party tools that you can use, but
there's third-party tools. What do you think? No console? Right.
Pretty much.
Also looking at the breakdown by beacon type, XHR beacons were by far the highest. 95% of them were XHR beacons. So we basically were looking at XHR beacons from IE7 or IE9, specifically hitting an API. And so from our raw data, we found that the IE7 and IE9 were the problems. It's easier to debug on IE9, so we went down that route. So how do you test with IE9 or IE7 or IE8? Who's used modern.ie before? Right. The rest of you need to go and have a look at it. Modern.ie is this great resource that has virtual machines of every single Internet Explorer version that's been released
Supported
on
by
every
Microsoft.
operating system that it works on. Yeah, every supported one.
Well, supported by Microsoft too. It's an official site from Microsoft.
So you can get like IE9 on Windows XP, or do they have Windows ME as well?
I don't know.
So they have every combination of browser and operating system. So if you know that you can reproduce a bug, or the bug is happening specifically with one combination, you can go and fetch that particular VM and test it out there. So this helped a lot. We fetched the IE9 and IE7 VMs and started testing out with that. So we set the VirtualBox with the IE9 on that particular host and just left it because this was happening with a single page app. We needed to see what happened over a period of time. And we started watching the traffic. So again, you use a tool like Fiddler because you're using, with IE9, you can look at the network toolbar. If you were using IE7, we would have to put Fiddler in the middle there and have a look at what's happening on the network. So just sit there and stare at the screen and see what's happening. And very interestingly, pretty soon we started seeing that these requests that were going out for the config object were showing up in Fiddler or in the IE9 developer tools with that little stop sign out there, which basically says the request was aborted. Right? So why was the request aborted? Because we looked at server logs and there wasn't anything to say that the request was being aborted. So why was the browser actually aborting the request? And this goes back to the fact that we were cleaning up. So this was Fiddler, right?
This is IE
The first
DevTools
one is
now.
Fiddler.
Yeah.
This one is IE9 DevTools. So we see the same thing here, that it's being aborted. IE9 actually shows you aborted in there. So why was it being aborted, and why did it happen after we started cleaning up these particular nodes? Because we were giving it enough time to download. It turns out that in some cases, IE9 has not downloaded it, even though IE7 has not downloaded the object, even though it's had enough time. And this is probably because it was blocked in some other resource. Maybe all of its allocated number of HTTP connections were used up, and it was waiting for something to free up before it could download something. So essentially, whenever we cleared that node out, if there was a request was still pending, it would abort that request. So we realized we could not actually remove the node until we had fetched a new version of the thing. So it was a timing issue. We were removing before fetching the new version. Now what we decided to do was fetch the newer version and only then remove the old version. So as soon as we started doing that, it started working. But in order to figure out what the problem was, we had to use a virtual machine with the particular version of IE and use Fiddler in place there because IE7 has no dev tools. And we could even do the same thing to test on IE6, or do they have IE 5.5?
I don't think so.
I don't have users with IE 5.5, so it's fine.
Okay, who uses Windows? Okay. Who has to deal with problems on Windows? Yeah, okay. Yes, yes. Okay, so I'm not going to go into the backstory of this as much just because we're running out of time a little bit, but we were seeing an issue. We had a customer to contact us because in IE Edge on Windows 10, right after it released, they were finding that the browser was hanging around the same time that we were submitting the beacon back to our analytics server. And so obviously we take this like really seriously, right? We do not want to screw up with our customers' sites or our customers' pages or browsers or anything. When we had tested Windows 10 technical preview like a week before Windows 10 was released, and we didn't see any issues at all, so we didn't know what was going on. So we were able to reproduce this actually right away. Loaded up Windows 10, loaded up Edge, went to the customer's site, and the browser hung for 30 seconds. The problem is when the browser hangs, the debugger is really hard to use. You can start it beforehand. We couldn't actually break into it when the browser was hung. You don't really get a lot of details afterward. And even the performance monitor wasn't really highlighting what was going on. So we're actually going to dive into system level tracing. Have any of you used event tracing for Windows or heard of it at all? Like a couple of people. Okay. So event tracing for Windows, it's built into Windows all the way back to Windows XP. It gives you a system level overview of what's going on. Very lightweight. It provides everything from CPU, what's on the CPU, to disk, to network activity, and even application events as well. So there are events that Internet Explorer and Chrome and other applications generate during the trace, and you can later visualize these. The Windows Performance Toolkit, which is part of the Windows deployment, I think. Do I have it down here? The Windows Assessment and Deployment Toolkit is how you get this. And here's what it looks like. So you take a trace, just like a PCAP file or something like that, but you're actually tracing for the system. And then you can later analyze it, load it up in a visualizer. And there's a couple different visualizers for it. You get everything, CPU, disk, hard faults, DPCs, TCP data, sample profile data. So you can actually see what was happening on stacks at every 10 milliseconds, or actually 100 microseconds on the machine. And so it can be really, really powerful.
And user timing as well, right?
Yep, and you can actually generate your own events as well, that if you want to mark specific events in the timeline. It's for free. It's built into every Windows OS. You can actually use it in a VM too, so if you have problems, you can use it in a VM. And there's some friendly interfaces for gathering traces, kind of like Wireshark makes it really easy to gather a PCAP trace. There's this UI for ETW from a Chrome developer for gathering traces as well. You can do it from the command line if you want. There's a very simple xperf -on, and then you tell it what kind of events you want to capture. Latency is everything from CPU to disk, and I think there's some network activity in there. You run your scenario, and then you stop. And at that point, the file is saved, basically, as an ETL file on the system. And then you can load it up in a viewer. So this is xperf view. It's a timeline. Each of the different graphs is something different. And you can overlay them on top of each other. This is just the default view. The top one, CPU usage over time. There's disk activity in the middle. I think there's some DPC usage in the bottom. And there's so many different data sources here, and you can combine them and overlay them and mix them and stuff like that. Even more powerful is you can zoom into specific regions and look at a summary table. So a summary table is basically a chart, an interactive tree chart that you can look at that gives you the breakdown of the data that you're actually looking at in numerical form, all the raw data essentially. So in this case, after looking at the CPU data, this is a breakdown of per process, how much CPU time it spent. And you can actually dive down and get, let's see, do I have it next? Okay, I'll go to that in a second. Not only system level data, but Internet Explorer and Chrome both also generate events. So in this case, this is the navigation start and stop. Anytime you're navigating anywhere, IE is going to say you started navigating, and then when the onload event fires, it's going to fire an event as well. So on your system level view, you can see exactly when there was navigations.
Start and stop there.
There's a bunch of other IE events. There's actually like several thousand of them. Everything from paints to layout, start and stop times for a lot of these. There's frame events, so whenever the user is interacting with like the bookmarks or the back and forward button, events are generated as well. They're not very well described externally, but you can look at the name and they kind of make sense. And you can also log your own marks in your own measures. So have you guys used user timing at all? No, not many. Okay. So user timing is a way in modern browsers to log a mark, an event, a timestamp in a standardized way. Browser developer tools will also show this. So if you're capturing a scenario, you want to keep track of how long something's happening, you can do a mark at the beginning and a mark at the end, and you can measure that time automatically. This data also goes into the ETL logs. So any user timing events that you're doing will also show up in these logs as well.
So it's important to note these user timing events do not work with the user timing shim. It has to be the built-in browser's user timing API.
But I think honestly the most powerful thing about ETW is you can get stacks, like actual stacks of most of these events that are generated, including CPU sampling. So the CPU sampler, you can have it run like every 100 microseconds, and you can get the actual stack of what was running on the CPU at that time. I apologize for how hard this is to read over here, but then you can actually sort by the top CPU stacks on your entire system and look at where activity was being spent. Now, there are public symbols for Windows, for IE, for Chrome, and Firefox. They're not going to have a lot of the debug information, but the public symbols will tell you what was on the stack at that time, the name of the function. And just by looking at these function names, you can actually kind of get some hints to what's going on. So there's a lot of ways to use ETW. Everything from, if you have a performance issue, you can just log a trace. look at the data. If you're doing, you could do automated performance regression analysis. You could launch, if you're publishing your website every day, you could actually take ETW traces and see if it's making the browser slower because you're doing more things with it. There's many, many ways of using ETW. And in this case, I used it to actually figure out what was going on the system when the browser was hung. So I loaded up Edge. I went to the customer site. I had started a trace beforehand, waited for the browser to respond again, stopped it, and loaded it up in the viewer. This line that you see here is the CPU usage of Edge specifically. So you see from here to here, we're at about 80% CPU usage of Edge, and this is over a period of 73 seconds. So Edge was actually just trying to do something for 73 seconds. That's essentially what it is. So zooming into that area.
Somebody changed code after QA and before production.
Which is even scarier, right? So using the public symbols from Microsoft, this isn't anything proprietary. This is stuff you can download from the internet. I looked at the summary table. It was actually, in this case, 82.9 seconds of CPU total. I just expanded the tree of where it was spending the time. And I think down here, so 65 seconds of that was this one stack. And you can't read it, but it says XSS filter, so cross-site scripting filter, on a lot of these function names. So whatever we were doing, we were convincing Microsoft that we were like hacking ourselves or something for 63 seconds.
I think it's important to, we weren't convincing them for 63 seconds. They took 63 seconds to determine if it was an XSS or not, which in any case is a bad thing to do.
Yeah, so we're running out of time, but at the end of the day, we actually sent the stack to Microsoft, and it's already fixed, thankfully. You can share exactly the issues that you're finding. It should be fixed in the next version of IE. We actually had to make some workarounds so our script didn't cause this bad behavior, but it was bad code on their side. But we have to work around it because we want to run in every browser. So those are the tools that we use. We have links in the slides. We don't have our names here. I am Nick J, N-I-C-J on Twitter, and I'll tweet out the deck. Blues Moon, B-L-U-E-S-M-O-N.
Yep. Is it on this list?
I don't think it is. Maybe. No.
All right.
One to the left.
We didn't put our Twitter handles there.
So that's it.